Hello, my name is Oskar Melin, and together with my team members David, Oskar, Mina and Ying, we're team MIPE competing in the LINHAC competition, in which we have looked at extracting patterns for controlled exits in ice hockey. In this presentation, I'm going to present the background for our project, followed by our motivation, and then I'm going to describe how we approach the problem, and I'm going to finish the presentation by showing our results for the project. There are two reasons why we decided to do what we did in the end. We found an article saying that teams that excel in the neutral zone are creating the most opportunities, so the neutral zone is an important one in ice hockey. And the way to get to the neutral zone is by having a controlled exit. So having a controlled exit may have a huge impact on the final score of a game, but this is often overlooked as most people are interested in shots or goals. As I mentioned on the previous slide, the neutral zone is an important zone, so we wanted to look at how does a team get to the neutral zone from the defensive zone in the best way. And a natural consequence of this was to look at where the most passes are made that lead to a controlled exit. In the data, we only looked at successful and failed controlled exits that occurred during 5 versus 5 play, so we did not look at box play or power play. For the successful controlled exits, we looked at two different sequences: a pass followed by a reception followed by a controlled exit, and a pass followed by a controlled exit followed by a reception. We did this in order to not capture sequences that were too long, since there can happen many things in a short time period in ice hockey. For the failed controlled exits, we also looked at two sequences. The first one was a pass followed by any event followed by a controlled exit, and the second sequence was a pass followed by a controlled exit followed by any event. If we compare the two, we look at reception for the successful exits and any event for the failed exits. This was because we noticed in the data that for failed exits, they were often considered to have failed since there was something blocking the reception from a pass. And one can imagine a pass made from the defensive zone that is blocked by an opponent and not reaching the intended player will be a failed exit. After we had captured all the data, we looked at from where the pass were taken and where the following event occurred. When we had all the coordinates for this, we used an algorithm to group the data, so we only look at the positions where many events occur in order to make it a bit more general. So this is the result for the successful exits. The left image tells us from where passes are taken, and the numbers in the bottom of the image tells us the position of the ice hockey field, where 0,0 is the center, and we believe that -25 to 25 are the blue lines. So we can see that the neutral zone is somewhere between -25 to 25. The colored points in the image tells us where the most common passes were taken, and the gray points are passes made that were not very common from that position. We can see that most passes leading to a successful exit are taken quite high up in the defensive zone, both towards the sides but also in the center. Some successful passes are taken from the back of the defensive zone, but only from the sides. Moving to the right image, which represents the reception of the pass, we can see that almost all receptions are down towards the sides in the neutral zone and spread out from the start of the neutral zone to the end of the neutral zone. Now we look at the passes made that led to a failed controlled exit. And looking at this left image, we can see that the passes leading to a failed exit are taken from the sides, going all the way from behind the goal all the way up to the blue line. In the right image, we see the event occurring after a pass for failed exits. And here we can see that many of the events occur towards the sides of the field, going all the way from the start of the neutral zone, all the way quite deep into the offensive zone. Comparing the successful exits with the failed exits, remember that many of the passes leading to a successful exit are more often taken higher up in the defensive zone compared to the passes leading to a failed exit. And we can also see that it seems to be difficult to make a pass straight into the offensive zone. In this image, we have all the passes taken and the following events, but this time we show both failed and the successful in one image. And we can also see the direction of the pass this time, and here we get a more clear image of where it might be best to make a pass. And as I've said in the previous slides, many of the passes leading to a failed exits are made deeper into the offensive zone. Looking at the most passes leading to a successful exit, we can see that these are passes made from the middle or end of the defensive zone. Some are diagonal passes, but most of them are just straight short passes into the neutral zone. And some concluding remarks from this could be that in order to have a controlled exit, it's much easier if you do it higher up in the defensive zone, towards the sides, and also somewhere in the middle, and to make these passes short and straight somewhere in the neutral zone. Thank you for listening.
Hello everyone, my name is Chayan Shangraj and I am studying Masters in Statistics and Machine Learning in Linköping University. I would like to thank all the jury members for selecting my work and letting me present here. Also, I would like to congratulate all the finalists present today and wish them the best. So, when I came from India to Sweden, I had no idea about ice hockey, how is it played and how many players are in the team. I had no idea about anything. But what I had was passion for data. So when I heard about this competition that is hosted in Linköping Analytics Hockey Conference, I was really excited about various things. Firstly, I would learn about a new sport since I'm an athlete, and second, I wanted to use my data science skills on a real world data set. So then after I watched a lot of hockey matches, ice hockey matches here in Sweden, and once I went also to Saab Arena to watch the hockey match, and I read about the rules, about all the techniques, the strategies. So the one thing I asked myself about the one question, that how can I make a solution that will impact everybody associated with this sport. So that's how I boiled down my solution to, since it all depends on how a player plays in the field, right, at the end of the day. So the data that was given to us was already in a good condition thanks to sport logic. So I focused my attention to how I can divide my data into training, validation and test sets. So I decided to divide it by the matches and all the time stamp in all the matches. So one match could be 60 minutes long, one could be maybe 65 because of the penalty and everything. So that's how I did that, and then I chose the outcome of a player's action as my final target variable. So since the outcome could be a successful outcome or a failure outcome, so it was a supervised classification learning problem. Then I used very powerful residual deep neural networks and ensemble of classifiers to predict the player's actions outcome. And it was a challenging task to implement everything in one, but it worked, and after a lot of brainstorming it worked, and I achieved an accuracy of 87%. And an F1 score is tells us how precise and accurate our model was 0.97, so which was a very good result. And then so now the question comes, how it helps the players, the teams, and everybody associated with this sport. So now, as we can see in the screen, so imagine if we apply our algorithm on this match, and then if this player passes to this, and then our model will predict if it will be a successful outcome or it will be a failure. So, and then I think this is a really powerful technique. So, and if we look at how it can help the players in the field. So any player, if it knows like how many of their shots are successful and how many are failures, and then they can improvise their own gameplay. It's not about they have to cut something about their or maybe change their gameplay. It is about enhancing their own gameplay. And then they can also improve passing strategies because they already know, they have seen their matches, and then they know about, and then they can augment the data also, and then check all the permutations of how these passes are successful or failure. So it can improve in passing strategies, and then finally it can help them improve the implementation. They can execute their pass with finesse. For the coaches, this could be, so it can help decide the coach that which player is good or bad at which area of the field, and then it can be used to decide the position of the players. Also, since our data set was about both the teams, about the timestamps of both the teams, so we also know about how well the opposing team is doing. So that's also, we can know about opposing team game also. So we can learn from them, or maybe we can better our game during that. And then we can also reinvent new techniques about what is going wrong with our game, or what is going good with our game, and then overall it would be really beneficial to many people associated with this game. And I thank you once again for letting me present my solution here. Thank you.
Hello everybody, welcome to my presentation about the effect of shot location on rebound quality. So before we get started, I just want to make a note of the coordinate system used. It's based on this chart in the left hand corner. The offensive zone extends from 30 to 100 horizontally, and from 45 to -45 vertically. So a little bit of motivation as to why we want to generate these high quality rebounds. As you can see in the top right corner, it shows the expected goals from first shots based on their location. So what we're seeing kind of makes sense to what we would expect. The closer you are to the net, the higher you are for expected goals. The further you are away, the less likely you are to score. However, when we move into this bottom corner here, we get a similar effect. This is for rebound opportunities. It's the same pattern where the closer you are, the more likely you are to score, and the further away you are, the less likely you are to score. However, you're almost twice as likely to score from a rebound shot than you are from a first shot. So this brings us to the question, where can we shoot from in order to generate rebounds of high quality? So if we want to be able to improve a team's offense, first we have to know how they currently behave. So seen on the left is a chart of shot frequency based on location. And it's also what you'd expect. You see most teams shooting from in the middle in the slot, and as you get to the outside, you see less and less shots. You also see these, you can see where the corners are, as they don't shoot from these areas that are blacked. So this matches up with the chart that we saw earlier of expected goals from shots, which isn't a bad thing. It means that teams are shooting from high expected goals areas, but this can be improved through the use of the rebounds. So now we can get to the results of the research. So seen in the top left corner is a chart that shows the expected goals of a rebounded shot based on where the original shot came from. So to explain a little bit more in detail, if you take this yellow hexagon here, it means that shots from this area generated the highest quality rebounds, while shots from these darker hexagons generated lower quality rebounds. Kind of tell us where the best locations are for these high quality rebounds. But you can also see that there's a lot of white space here, and this is due to the fact that there weren't too many games to work with in the data set. So in order to make this a little bit smoother and easier to see, I only considered the distance to the net. And that's seen down here in the bottom left-hand corner. So we can see that the best place to shoot from is this area in like the slot and the hash marks kind of distance from the net inside the circle. It's also a good idea to shoot from the point. So these areas in red is where you will be generating the highest quality of rebounds. There is like a no man's land here, this blue area at the top of the circle. And teams shouldn't be shooting from here if they want to generate these high quality rebounds. A little bit what surprised me was this area down here close to the net. But when you think about it, it just means that shots close to the net aren't generating the high quality rebounds. This isn't saying that shooting from close to the net is bad. Teams should still shoot from close to the net as much as they can, based on the expected goals chart that we saw earlier. So to sum it up, if teams want to generate these high quality rebounds, they should shoot from the areas in the slot and inside the circles, as well as shots from the point. Looking ahead, there are a few things that can improve this research. Because this research was about rebound quality, the next thing that we should consider is the rebound quantities that are generated and where we should shoot from in order to get lots of rebounds. Another thing that could help improve this study is to get more data from more games. This should fill in the white space from those graphs and provide better results. And that's the end of the presentation. Thank you everybody for watching and have a great night.
Hello, welcome to my presentation today. I'm going to talk about my solution for the LINHAC student project competition, and the title of my project is Sequential Ice Hockey Event Generation Using the Generative Adversarial Network. My name is Mohammad Fahim Shikdar and I'm from Linköping University. So if we look at the contest problem statement first, here we have to generate or find the pattern events that leads to a particular outcome given the data. And for this project, we have used the Swedish Hockey League data that contains 20 matches provided by the Sportlogic. Sports analytics can be used by the management level of a team to devise tactics. For example, in hockey, we can learn what steps to take for a particular outcome or determine player performance. In this project, we used hockey goal as a targeted outcome and generated sequential events and coordinates leading to that. Our solution for this problem was to learn a generative model. We have used TimeGAN, that is time series generative adversarial network, to capture the pattern of the original data and create a synthetic version of it. We showed the sequence of events that leads to a hockey goal from the synthetic data and plotted the coordinates of these events in a hockey rink. The reason behind using the generative model is that it can capture the pattern of the original data. Also, the generated data follow the same distribution as the original data. Again, sometimes the size of the original data can be small. For example, the data we are working with has only 106 goals, and it might be difficult for other machine learning method to learn pattern from the small amount of data. So, by using generative models, it is possible to sample unlimited amounts of synthetic data. Now for the training approach. First, we need to pre-process the data to make it compatible for the model, then use the TimeGAN to learn the pattern of the original data and make a synthetic version of it. Then find the goal events from the synthetic data and show sequential events leads to it, and finally plot the events coordinates. The architecture of the TimeGAN consists of 4 modules: the encoder, decoder, generator, and discriminator, and it used 3 different loss functions. These functions also help the TimeGAN to overcome mode collapse problem. We have implemented 3 generative models, TimeGAN and 2 variants of least square GAN, LSGAN, and evaluated the synthetic data generated from these 3 models by using PCA plots and with a sequence prediction task where we take the first 23 sequence as input and try to predict the next one. Here we can see the PCA plots of 3 generative models. Each dot here represents one sequence of data, and blue dot represents the original data, and the orange one is synthetic data. If a generative model learns the distribution perfectly, the blue and the orange dot would overlap. Here we can see that the TimeGAN learns distribution better than the other 2 models. We have also evaluated the synthetic data using a sequence prediction task. Given 23 sequences, predict the following sequence. We trained a recurrent neural network with synthetic data and test on original data. This process is called train on synthetic and test on real. We evaluated the mean absolute error and mean squared log error for the task, and TimeGun shows better performance. We sampled 140,000 events using the TimeGun and showed the heat map of goals using different bin calculation technique. In the upper figure here, we have shown the heat map of the goal where we have counted the goal events in each bin, and the lower figure here shows the heat map where we take the average of the goal events. The amount of goal in the original data was 106, but in the synthetic data the amount is more than 7,000. Here in the lower figure we can see, even though in the original data there is no goal in this area section, but synthetic data captures the pattern and generated these goal events. Here in the left figure we have shown the 4 individual sequence of events that leads to a goal. The G represents the position the goal is scored, and the right figure shows one individual sequence of events and their corresponding coordinates. These are all synthetic data. So the main contribution from us is the idea of using generative models and synthetic data for this project. Also, the approach we have implemented here is generalized, so it not only works with the goal pattern finding but also can find other patterns such as zone entry. And to our best knowledge, this is the first work where synthetic data has been used in hockey analytics, and the code for this project can be found here. As our solution is generalized, it can be used to find different patterns for specific outcomes, and it is possible to sample unlimited amounts of data. And also there is event plotting and heat maps. So we believe these features might help hockey analytics to make a decision. Thank you so much for your time today.